we are very delighted to have Chris Desert here with us, who just landed coming in from New York. So Chris did his PhD at Michigan State with
Michigan. It's all good.
Yes, University of Michigan with Ben Safi, and now he's a postdoc at Flatiron Institute in NYU, and he'll tell us all about the cosmic Axiverse. Please.
Thanks. Yeah, very happy to be here. I'm super jet lagged, so if anything is less than clear, then I apologize. So this is based on some work that I think will come out this month with Josh Ruderman and Shobhit Kumar, who are a faculty and postdoc at NYU, respectively. And I'm going to be talking about a relativistic background of radiation, particularly of axions, that might be present in the universe today, kind of analogous to the cosmic microwave background shown here, and which we will be able to look for using the cosmic microwave background. So it's always good to start with what we know, the standard model. So nature is described by a set of internal symmetries, SU3 color cross SU2 left cross U1y. And the set of particles that we've observed, recently capping off the standard model with the discovery of the Higgs. And this collection of symmetries and particles tells us essentially how to calculate everything below and at the weak scale. So we think we potentially know the nature of electroweak symmetry breaking. We can calculate the electron G-2 to something like 1 part in a trillion, and do a whole host of other very accurate calculations that have all been borne out by almost all of the data that we see today. One outstanding puzzle is the nature of dark matter, which we know to exist in the universe. It makes up about 5 times more energy density than the ordinary matter we're made of. And we know this from, for example, observations of rotation curves of galaxies, but also through the cosmic microwave background, CMB lensing, and so on. So this is an observational misunderstanding that we have of the universe. On the symmetry side, there's a set of space-time symmetries as well that we can categorize physics under. So we have charge conjugation symmetry C, parity symmetry T, or parity symmetry P, and time reversal symmetry T. And the combination of charge and parity we don't understand. So there's a CP problem in the standard model, which is essentially that we don't seem to observe CP violation in the standard model. So just to remind you a little bit about what CP violation in the standard model looks like, there are 2 contributions. One is from the weak sector, so there's this CP violating phase in the CKM matrix, delta, and there's CP violation in the strong sector through this angle theta. So the weak CP violation we've known about for some 70 years through observations of kaon decays, and delta has a value of 1.2 radians. It could take on any value between minus pi and pi. So this sort of seems like a reasonable number if you had to just guess it was randomly chosen. But this doesn't turn out to be the case in the strong sector. So strong CP violation, people have looked for a while. It would enter the Lagrangian of the universe through this term theta, this angle, times GG tilde. And one of the things that this leads to is a non-zero electric dipole moment. So I've taken this picture from Anson Hook's TASSE lectures. It's a classical picture of the neutron as 1 up quark and 2 down quarks, and theta is the angle between the up and down quarks here. And so even from this classical picture, you can kind of estimate that the neutron electric dipole moment should be something on the order of 10 to the minus 16 times theta in units of E centimeters. And then you can go and look for this out in the laboratory. And you find that apparently the neutron looks something like this, where all the quarks are aligned. So empirically, theta has to be less than about 10 to the minus 10. And this is a huge unexplained tuning of the theory if theta is just some parameter. So we would really like a dynamical mechanism that tells us why theta should be so small, especially given the fact that delta seems to be large. So CP violation is not a good symmetry of our universe.
So when you say theta, this theta that you put in the previous picture, does it actually include the determinant of the
That's right. Really, theta here means what people typically call theta bar. Yeah. That's right. There's also an argument of the determinant of the quark mass matrices. So here I'm showing the limit on the neutron electric dipole moment as a function of the year of publication. And one interesting point is that the first experiment to look for the neutron EDM was performed in, I believe, 1957. And it had a sensitivity that if theta was order 1, we would have immediately discovered the neutron EDM, and this would have actually been the first observation of CP violation in the standard model. Weak CP violation was not discovered until experiments 7 years later in 1964. So the strong CP problem is sort of succinctly characterized by the question, why do the strong interactions conserve CP while the weak interactions maximally violate CP? And there's a good solution to this puzzle, which one can get to by promoting theta to a dynamical field called the axion. So this mechanism is called the Pesci-Quinn mechanism. You take your theta here, coupled to GG tilde, and you promote it to a dynamical field A, the axion. This is a pseudoscalar, dimension 1, so it needs to be divided by some mass dimension. Fa is the decay constant, and basically describes all of the couplings of the axion to other particles, including the standard model. And the ingeniousness of this mechanism is through the fact that after QCD confines, this term GG tilde essentially gives a potential to theta, which schematically looks something like this. It's a 1 minus cosine potential, but here I'm imagining I'm just zoomed in around the minimum. So if early on the universe is at some order 1 CP violating value, theta CP violating, then when QCD gets a potential, this now dynamical field will roll down that potential and get set to 0. Or really, theta, the effect of theta will get set to 0. The axion field will get set to minus theta times Fa. And so this sets the neutron electric dipole moment to 0. You also get dark matter for free. So oscillations around the minimum of this potential correspond to dark matter excitations in the universe today. And they're very small oscillations. In units of theta, they're order about 10 to the minus 19 today. And looking for AC oscillations in the neutron EDM is one way that you could imagine looking for evidence of this axion. But the interesting thing that I want to focus on is that this axion is actually extremely light. So you can just compute the second derivative of the potential, and if you want the axion to be dark matter, then you find that you require that the axion mass has to be about a micro EV for a decay constant of 10 to the 12 GeV. And so this is extremely light dark matter. It's produced completely coldly through this kind of vacuum misalignment mechanism, so there's no issue with warm dark matter, even though it's very light. But on the other hand, you could imagine that some component of this axion field gets thermally produced through interactions with the standard model that it might have, potentially at very high temperatures, sort of close to the scale FA, because all of the interactions are suppressed by some very high scale. And generically, this is something you can have with any light particle coupled to the standard model. So if you have some sort of light relic, by light here I mean typically with a mass less than an eV or so that it's relativistic at the time of the CMB, and we'll see why that's important. Then you can thermally produce these particles if the universe gets hot enough. So here there are kind of three regimes. I'm imagining some process taking place in the early universe far above the electroweak scale and of course far above the scale today. So there's this parameter gamma int, and that describes the interaction rate of your particular light relic, just some particle, with the standard model bath. And if this is ever larger than the Hubble scale, then interactions between the standard model and the light relic can happen efficiently. And you will thermalize that relic. You'll produce a thermal population with a temperature equal to that of the standard model bath temperature. Now, the universe is expanding, and so as the universe cools, gamma int typically goes like some high power of T relative to the T squared the T squared scaling of the Hubble parameter in radiation domination. And so as the universe cools, gamma int will fall faster than Hubble, and you'll eventually reach a particular temperature called the decoupling temperature, where these two parameters are equal. And below that, gamma int is so small that you aren't able to keep that population of light relics in thermal equilibrium with a standard model. Let's see. Good. Yeah, so you end up having this condition where if the reheat temperature of the universe, so essentially the highest temperature that is ever achieved after, say, inflation or maybe a matter domination era, is larger than the decoupling temperature, then you produce a thermal population of these light relics that stays around today, even after it decouples from the standard model bath. And that's something, as we'll see, that you could look for. On the other hand, if the reheat temperature is smaller than the decoupling temperature of this particular process, then you, yeah.
So these actions, so don't they contribute to the anisotropic stress loading in response to decoupling?
Yeah, so typically the strongest constraint you'll have from the strongest constraint that you'll have from having light particles around is from ineffective. So looking for, radiation density, contributions to the Hubble parameter essentially. And yeah, that's what I'll be doing. Yeah. I'll get to that, I think, on the next slide. Yeah, good. So in this case, where the reheat temperature is smaller than the decoupling temperature, you don't produce any particle bath. Good. So for a generic light relic, if you produce it in a thermal abundance, then it will contribute some dark radiation energy density at the time of the CMB. And this will increase the Hubble parameter because it's a contribution to the energy density of the universe. Particularly, we parameterize this as ineffective. So ineffective in the standard model, its value is 3.044, and a value of 1, this is just a normalization of radiation energy density. So a value of 1 corresponds to the value that, the energy density that a single standard model neutrino contributes to the radiation density of the early universe. It's slightly larger than 3 because of non-instantaneous decoupling effects and like QED effects and so on, but it's essentially 3. However, if you have additional dark radiation around, such as this light relic, then it contributes to this parameter we call delta ineffective, which is just anything additional. And you can compute as such. The normalization parameters here are essentially, here I've normalized it to the CMB energy density. There would be no normalization parameter if I had normalized it to 1 neutrino. So you can go through a calculation and you find that if you have a boson decoupling above the weak scale, then the delta ineffective that you produce is equal to this number. So 106.75 is G star for the standard model at very high temperatures. 10.75 is G star at the time of neutrino decoupling, but the details don't really matter. The point is that the contribution to delta ineffective you get from a boson decoupling is this value will keep returning to 0.027 times the number of degrees of freedom associated with that dark radiation. If you decouple below the weak scale, then you run into G star effects in the standard model, and you can get potentially higher values of delta ineffective. But for what I'm going to be doing, I'm just going to assume everything's going to happen above the electroweak scale. Most of the parameter space, this is a good assumption. And it's an interesting time to be thinking about the CMB, because if you're looking for light relics through delta ineffective, the Atacama telescope just a few months ago had their final data release, and they put a constraint on delta ineffective of 0.17. Ongoing efforts in Chile with the Simons Observatory are going to improve these constraints by a factor of 30% or so. And then maybe we'll get lucky and CMBS4 will happen in the sort of near term, which would get us down to extremely small values. And in terms of the number of degrees of freedom you could probe with delta ineffective, you already can't have more than 6 scalar degrees of freedom in equilibrium with the standard model if they decoupled above the electroweak scale. With ongoing telescopes, we'll get this down to 4, and in the future we could get this down to 2, and potentially with something like CMB-HD, we could get down to the parameter space where if even a single scalar was in thermal equilibrium with the standard model, at high temperatures we would know. So it's an interesting time to be thinking about this kind of thing.
So here, light relic is effectively acting as what happened?
Well, so specifically relativistic.
Yeah, that's like what happened.
Yeah. Yeah, it has to be relativistic because it needs to contribute in large quantity to the CMB energy density. Yeah. So now thinking about specifically the QCD axion, it has an interaction rate. So the QCD axion is what I've been calling the axion so far. It's the one that talks to GG dual. And it has an interaction rate, which you can compute from these diagrams here, of about alpha strong cubed, T cubed over FA squared. And if you want this to be larger than Hubble, you find, well, with an inequality here, you find that the decoupling temperature for a QCD axion is about 10 to the 12 GeV for a decay constant of the same value. And so,
One question from the previous slides. The central value that you said is 3.04 or something. So the delta and 95% is basically away from that.
that's right, yeah.
So
That's assuming the standard model.
You have 6 extra things on top of the
Right. Right, that's assuming the standard model value. Yeah. And we have agreement between BBN delta ineffective and CMB delta ineffective. I mean, the neutrinos decoupled essentially at BBN, so you could get rid of the neutrinos between BBN and CMB potentially, but I suspect it's kind of hard to do. So yeah, I'll be assuming that the standard model value is this 3.044. Good, so if the reheat temperature was ever larger than this value, then we get a delta ineffective of 0.027. So this is something you can't see, even with CMB S4. But what I want to think about is not if you have one QCD axion, but I want to think about a larger class of scenarios where you might have many hundreds of axion-like particles. So in the context of string theory, there's this notion called the Axiverse. And so in string theory, you have 10 dimensions, and you have to compactify those 6 of those dimensions down so that we observe the 4 that we live in. And in that process, there are gauge fields that live on this 10-dimensional volume. And yes.
That must depend on how you are even computing the pitch.
So yeah, I mean my UV completion is all wrapped up in FA effectively, but it could depend in principle on, yeah, I mean if you have like a KSVZ UV completion, then there could be heavy quarks that would change this picture. That's right.
Or TFSZ, so that
Yeah.
this 0.027 must depend on that. Maybe weakly dependent, but
Yeah, it's, well, so when you, as long as you decouple above basically the top quark mass, you get this 0.027 essentially independently of when you decouple. And it's just because G star is not changing above the electroweak scale. Now the decoupling temperature could depend moderately on, or even potentially a lot on this particular UV completion. I'm going to be, for this talk, I'm just going to be assuming that the EFT description always is perfect. But in principle, yeah, there are like some details we could talk about. So in KSVZ, actually the decoupling temperature could be a few orders of magnitude lower. Good. Yeah, so in string theory, you can get many hundreds of axions. Sort of a typical value might be 100, which arise from integrating out 0 modes of gauge fields, which live on essentially these compactified dimensions. And you have higher KK modes and so on that I'm not going to be thinking about. But it turns out that the axions that arise from these 0 modes are extremely light particles, pseudoscalar particles that act a lot like the QCD axion. So typically, if people say axion-like particle, they're thinking about axion, like pseudoscalar Nambu-Goldstone bosons that do not interact with gluons, and the QCD axion is the one that talks to the gluons, and that's kind of the nomenclature that I'll be adopting here. There are some recent empirical studies from a group at Cornell who were looking into, in explicit compactification scenarios, what spectrum of masses you get in the Axiverse and the spectrum of decay constants. Here they've looked over a variety of compactifications. N is the number of axions you get from the compactification. And you can kind of see that the axion masses are log uniform over a wide range of scales. And actually later papers they go down to, so here they cut this off at the Hubble scale. Later papers they go down to like machine precision, so 10 to the minus 300 eV, and kind of see this log uniform scaling all the way down. On the other hand, the decay constants you typically get from these compactifications are relatively similar among all of the axions. So I'm going to be working with an EFT framework, and I'm going to make some simplifying assumptions. These particles are generically very light, so I'm just going to set their mass to 0. If their mass is less than an EV, that's basically a perfectly good approximation. And I'm going to be assuming that there's just one decay constant that specifies, the strength of the couplings for all of the axions. And this will vastly simplify things. But the question I want to ask, of course, is, if we had just one QCD axion, then the contribution to delta ineffective was 0.027, this minimal value. But if you have many of these light particles, they each have interactions with the standard model, and in principle they could interact and thermalize with the standard model bath at some very high temperature. And they could contribute to the energy density and lead to an ineffective, which is this 0.03 times times the number of axions, which could be large. And I've already told you that in ax here can only be 6 to be compatible with existing data. So let's just look at a toy example where there are just 2 axions, just to get some kind of intuition for what this might look like. So let's imagine that I've written this this theory down in some arbitrary basis where my 2 axions are called phi1 and phi2, and for whatever reason I only have couplings to E and M. So each axion phi I is coupled to E and M with the strength GI. Yeah.
Because I've always seen these people and they say that these are axion-like particles.
Mm-hmm.
But why can't they? So when you're doing a string theory, presumably you're doing a complete particle. So why can't they specify the coupling of these axion-like particles to other standard particles? They just assume it's an A15 letter, as you said.
Yeah, so actually in a recent paper they did specify not all of the couplings, but the couplings to photons. So the couplings to gauge bosons are somewhat easier to specify.
But in the UV complete model, I would assume, without doing anything, that they should have it somewhere in there. Maybe it's difficult to...
I think, yeah. The gauge boson couplings are relatively easy, is my understanding. The fermion couplings are extremely difficult. I think in principle computable, but they have not done that, and they've told me that they don't know how. They don't know how.
So my understanding is that these models are, in general, they're not trying to phenomenologically they're not trying to get the standard model. It's
Right.
just some compactification where we get all the, it's a space of compactification that he hasn't specified that, but I think there's a space of Calabi-Yau or whatever that you can use. So in that, you get like this uniform spread of these.
Yeah, this is like the Kreuzer-Stark database.
But just like, what is the coupling for the standard?
So for that, you have to get the standard model processor. That's what I'm saying. So they are essentially what they do in these theories that they start with a unique coupling that we set up and get over the theory which contains all these gauge fields together with action-like particles. But the rest of the phenomenology is, I don't know what they do specifically in this case, but most of it they don't. They just leave it to be.
Yeah. Yeah, that's right. Good. Yeah, okay, so we have this toy example. These 2 axions independently couple to E and M. But of course I can do a field redefinition, just rotate the basis, and write this as a axion A gamma, which is the thing that couples to FF dual. And then I have a sterile axion, which in this vector space is just some orthogonal direction. It doesn't talk to anything. So if trying to create expectations for what I would see cosmologically, I would say that there's only one axion that actually talks to the standard model. So even if I kind of naively write the theory down in this basis, and I think, oh, they both axions couple to the standard model, so I should get 2 thermal abundances. When I write it in this manner, you can see that this particular operator only couples to one single axion state.
Why is it mixing perhaps? The 2 files?
Yeah, there could
Then the A perpendicular will not be sterile.
yeah, you could have like mass mixing or something in principle. Actually, I have some backup slides. We show that isn't important for ineffective. But in principle, it's there. Yeah, yeah. Good. Okay, so the kind of lesson, general lesson here is that you get this minimal contribution to delta ineffective per operator that couples to some linear combination of axions. And then I can rewrite this axion vector, if you like, in terms of one axion state that talks to this operator. And then the Ci phi I is the thing that interacts with the standard model and potentially thermalizes.
So is there a reason why just one of them is talking to the standard model? Can't they both talk to standard model?
Yeah, if you had, so good. If you had another operator here, like say put in a GG tilde, generically, I mean, unless you have some kind of tuning where these coupling constants are the same, then in that case, indeed, you would have two axions. They would both be talking to the standard model. And actually, we'll see this on the next slide. Yeah, good. So there are strong constraints on this kind of scenario. So we decided to look into it. So what I want to do now is essentially just this. I want to write down the axion effective field theory at dimension 5, working exclusively above the weak scale because this just simplifies things greatly. And the only particles I'm going to assume that I have around are in axions phi I, and then the standard model. And this EFT with one axion is known. It's written down in, for example, this paper, but with an arbitrary number of axions, it hasn't been ever studied. At least phenomenologically. Sorry? Good. Yeah. So this first term here, this is the coupling of the axions phi I, and just some arbitrary basis. And this is summed over all of the gauge couplings. Yeah. Yeah. So there's GG tilde, WW tilde, BB tilde. Yeah, so there's three gauge couplings you can write down, and then you can write down derivative interactions of the axions with the standard model fermions. So these psi here are the fermion multiplets of the standard model. There's 5 of them, and they have 3 generations. So the coupling, say Wilson coefficient of this operator is a 3x3 Hermitian matrix. So explicitly it looks something like this. The on-diagonal terms tell you about axion couplings which are flavor conserving, and the off-diagonal terms tell you about axion couplings which are flavor violating. And then there's an axion coupling to the Higgs current as well. Yes, I'm taking these FAs to be all of the same scale. To the extent that they aren't, you could imagine that I like reshuffled it into the Wilson coefficients, for example. And basically what you want to do is you want to go to some interaction basis like we did here. But this is impossible in this case because we have a large number of possible interaction bases which are all in principle misaligned. And so what you want is to create some orthogonal vectors in the axion state space. To do this, you can one way you could do this is to use the Gram-Schmidt orthogonalization procedure, just from undergrad linear algebra. You pick a particular vector. So say here I've picked the QCD axion because I think it's going to be important. And I just define that here as the thing that couples to GG tilde, as you usually do. And then it just has some arbitrary couplings to all of these other operators as well. And then I pick a second axion vector. So here, the one that couples to WW tilde. And I project out from that vector the QCD axion. so that it is orthogonal. And then it has couplings to all other operators except QCD. And I can continue doing this to create a axion vector space that is orthogonal. If I have more axions than I do have standard model operators, then I get some set of sterile axions at the end of the day. So I'm going to make a sort of simplifying assumption that for whatever reason, all of these flavor basis states happen to be orthogonal already, and I can just drop all of these couplings. That's not necessarily, or it shouldn't be a good approximation, but I'm only getting rid of interaction terms with the standard model, so in that sense it should be conservative. So now if I count the number of axions that could thermalize with the standard model, I have a large number of states. I have 3 axions that talk to gauge bosons. I have 9 times 5 is 45 axions that talk to fermions, and then I have 1 axion that talks to the Higgs boson. So that gives me 49, but I've overcounted, and the reason is there are some redundant operators. So for example, I can do this type of field redefinition, which is axion dependent. And for an example, a field redefinition proportional to hypercharge, I can set the axion Higgs coupling at dimension 5 to 0. This is the basis that people typically work in if you do like axions at colliders. But then I can set an additional 4 operators to 0 by doing B and individual Li lepton number rotations. Of course, this is only good up to the neutrino masses, but I'm assuming that those are small. And to the extent that these operators exist, they're not going to be important for any cosmological dynamics because they would be suppressed by neutrino masses. Yeah, 3. So there's one axion talking to gluons, 1 to W, and then 1 to B. Yeah. And then it's not so obvious, but if you do a B plus L rotation, then you can actually remove the axion that talks to SU2 left. Good. Okay, so we've overcounted by 5 operators, and actually there should be 44 independent axion states that talk to the standard model. And this is kind of cute because if you're an EFT person, you probably know that there's a big program for any particular EFT of trying to determine the number of independent operators that exist at a particular dimension in the EFT. And this is in principle a way that you can make a measurement and actually count that number. So, if all of these axions happened to thermalize, which is not the world that we live in, then you would be relieved to know that you only saw 44 of them and not 49. So, EFT is working. So at dimension 5, in the EFT, the summary is basically that each operator can thermalize an independent axion state. There are 44 of them, so we know that not all of them could have thermalized because the limit is that 6 of them could have. But not all of them were strong enough to thermalize anyway, so we shouldn't be greatly concerned. It depends on the C's, that's right.
So when you say not all operators are strong enough, that is effectively coming from CMB, right? Without CMB, you would not have said that. If you had known the limits of dependent, say for example.
Well, I mean, so even if I maximize the C's at, say, like the unitarity limit, you can already tell that not all of them would be strong enough to thermalize. So yeah, we'll see this in a second, but like the fermion. Well, yeah. So this strongly depends on your expectations for what the fermion couplings look like. So those C's, but the interaction rates are set by Yukawas. And so if if you're coupled to electrons, it's just not important cosmologically whatsoever, because that's a huge suppression. And we'll see that in a second. Good. So there's no calculation of axion fermion couplings that I am certainly aware of, or that the Cornell group is aware of in the Axiverse. So we consider a few scenarios, kind of benchmark scenarios for what these couplings might look like. One is a hadronic Axiverse. So this is just all of the axions only talk to gauge bosons. The fermion couplings are 0. Another assumption is flavor anarchy. A third is we have some Frogot-Nielsen mechanism. And finally, we're going to look at minimal flavor violation. So I'll come back to all of these in some detail. Good. So you can think of this hadronic Axiverse scenario as essentially every axion is a KSVZ-like axion. It has only couplings to the gauge boson. Only couplings to the gauge boson. So we're just going to get rid of these entirely. And remember, we've removed the Higgs term by a field redefinition. So there's just 3 axions that could only states that could thermalize because of these 3 operators. And we could further imagine that if the standard model at high energies is embedded into a gut, then somehow all of these axions are correlated. They all came from the same G gut, G tilde gut. And in that case, these vectors are just exactly aligned. So you only get one axion talking to the standard model. So I've already told you how to compute the decoupling temperature for an axion coupled to gauge bosons. It looks like this. This is just the same formula where I've normalized alpha to alpha strong, and it proceeds through these types of interactions. Okay, so on this plot, what I'm showing is a color diagram of delta ineffective, the contribution to radiation density from axions, as a function of the reheat temperature on the y-axis and the decay constant on the x-axis. And what I've assumed for the C's is that they're order 1. And I'm just going to assume for the gauge bosons, I'm just going to generically assume that. And so what you can, good. This white space here is exactly the space where the EFT breaks down, and I'm going to completely ignore that space. If you reheat above FA, string dynamics could take over. If the axion's like a field theory axion, there would be other states at that scale. So I'm not going to think about that. But here, what you can see is kind of along this line where this purple, which corresponds to 0 and effective, turns to blue. That's the decoupling temperature of the QCD axion. So at reheat temperatures above that scale, the QCD axion is thermalized and contributes at about 0.03 to delta ineffective. And you can see a few other transitions as well for the axion coupled to weak gauge bosons and to hypercharge. This particular scenario, you would need a future telescope like CMB stage 4 or even CMB HD to probe. And that's essentially just because there are so few states that you could populate that it's going to be hard to look for something like this. On the other end, if the standard model is embedded into a gut, then you would only get one state thermalized at essentially roughly the decoupling temperature of the QCD axion. Good. So now if we want to turn on fermions, the axion production rate is controlled essentially by this diagram. Time could either go this way or it could go this way. And the rate for axion collisions with the standard model is kind of order the C's times Yukawa's all squared, and then the T cubed over FA squared you expect from a dimension 5 operator. Good, and so if you put in an order 1 Wilson coefficient and an order 1 Yukawa, then the decay or the decoupling temperature for the axion is about 10 to the 7 GeV for a decay constant of 10 to the 12 GeV. So for something coupled to the top with order unity couplings, this is actually quite a bit stronger than for the QCD axion with no couplings to fermions. So the second assumption we're going to make about the fermion couplings of the Axiverse is that they are anarchic. So what I mean by this is that the entries of the C-psi matrices are just order 1 random numbers. On the off diagonal, there's also an order 1 random phase. And since these are just order 1 numbers, when you do this Gram-Schmidt decomposition, what you'll find is that every operator thermalizes a different axion. And so here you get a full 45 different axion states talking to fermions with order 1 coefficients. So this kind of messy plot, we're still workshopping, looks like this. I'm plotting now FA is still on the x-axis, but the decoupling temperature of each axion is on the y-axis. So what you see here is at very low decoupling temperatures, you have axions which are coupled to the top, which has a U.S.A of order 1. And remember, it's coupled with order 1 coefficients. So these are extremely efficiently interacting axions. You can't see it, but there's 10 axions here, and the reason is that the top U.S.A is felt by both the Q multiplet and the U multiplet, and then there's 5 entries of each C-psi matrix that talks to the top. So even the flavor violating axions that talk to the top will get a top U.S.A contribution to the rate. And then axions which are coupled to lighter particles are a bit harder to see by about 2 orders of magnitude. And then there's axions which are coupled to even lighter particles. The interesting thing about this parameter space, which actually has nothing to do with the Axiverse, but is just an interesting fact about kind of thinking about more generic UV completions where the axions have some flavor violating structure, which you might expect them to have, is that there are constraints from K plus decays to pi plus invisible, this NA62 experiment, which for order 1 flavor violating DS couplings has a constraint on axions down to arbitrarily low masses of almost 10 to the 12 GeV. And I think people don't think about this as much as they should because the kind of less model dependent constraint is coming from neutron star cooling or supernova cooling out at 10 to the 8 GeV, but 3 orders of magnitude higher, depending on the axion flavor violating structure, there are constraints that are extremely powerful. Good, so now I'm just showing the same plot, again, with reheat temperature on the y-axis. All of this parameter space is ruled out by kaon decays, but the recent ACT constraints tell you that even for extremely high FA, you could not have a reheat temperature which is kind of within a few orders of magnitude of the scale FA. Or you would thermalize all of these axions which have couplings to the top. And with future experiments, you could do about maybe an order of magnitude better than this in the future. I should also mention that we're working essentially explicitly in the pre-inflationary scenario. So if you want the QCD axion to be dark matter, then it lives kind of somewhere to the right of 10 to the 12 GeV. So in this parameter space, you might see some detection from ineffective of the Axiverse, and you could also see a detection of the QCD axion in some laboratory experiment.
In the old days, there used to be constraints from red giant cooling
Right.
and supernovae and stuff.
Yeah, so that should live here in principle. It's a little more model dependent, but it's around the same. It's around the same FA as neutron star cooling. Yeah.
So one is when you so in all these plots you're plotting the neutron star cooling as a vertical line.
Mm-hmm.
So that means so these string theory models don't predict the mass of the axion. All of them are distributed. All these. And then most of them are light, but are all of them light?
No, good. Yeah, so not all of them are light. Yeah, I mean, if we go back to that plot, there's actually quite a few that could be quite heavy. They need to somehow decay, and yeah. There are also cosmological problems with that, yeah.
Also, you're making for that kind of standard model coupled every possible action thing that you do.
Right, right.
So that's
No, but for the neutron star cooling, the axion has to be light mass.
right. I understand.
That's
What I'm
right,
saying.
yeah.
I don't know whether there's a string theory involved in this. Is there a direct string theory involved in this? In the axion? So is sort of like a
Good. So what this neutron star cooling curve assumes is, yeah, what I guess I'm assuming here is that there's a QCD axion, and it has some decay constant FA, and there are limits on the QCD axion neutron star cooling. And that is specifically what I'm taking here. So just through its interactions with gluons. There could, I think if you think about cooling from couplings to fermions, then I believe those are weaker. Yeah.
And what about upcoming binding experiments? Maybe similar to the
Yeah, I don't, the pion decay experiments are all living around here, I believe. I don't think I think they're running into backgrounds, so I don't think that they'll get quite here. Actually, this particular NA62 experiment, there's a standard model contribution to this, which is K plus to pi plus nu bar, which they just observed. So in principle, they're also background limited. Yeah, it's like a 1.7 sigma anomaly. I mean, in principle, yeah, if you're really optimistic, then like this is exactly where you expect QCD axion dark matter to be with an order 1 misalignment angle, and you know, I mean, that could be what they're seeing.
decay experiments are not very sensitive.
They're less sensitive. I don't know off the top of my head, but I computed all of them here and then took the most sensitive one and plotted that. Good. Okay, so that's this anarchic Axiverse model. We also look at a Frogot-Nielsen model. So this is some. Essentially, we imagine that there is a Frogot-Nielsen mechanism at higher scales than FA that solves the flavor puzzle. And what you do in the Frogot-Nielsen mechanism is you produce the Yukawas through the VEV of some scalar S. So this is the standard model Yukawas, and there's some U1 horizontal symmetry that the scalar is charged under. With charge -1, doesn't really matter. And you charge the quarks under this symmetry as well. And then just to get charge conservation, out in front, you need the VEV S to some power which is dependent on the generation indices of the fermions. And you model this such that you observe the Yukawas we see in the standard model. Now, given that, the interesting thing is if you look at axion fermion operators, you know, these psi, the different generations of psi are also charged under U1 horizontal. And what this tells you is that the coefficient C psi has to go like some power of this ratio, which is just the charge difference of psi I and psi j. So if the standard model is UV completed into some Frogut-Nielsen mechanism that explains the structure of the Yukawa couplings, then you immediately know that the axion fermion operators have some particular structure like this. So for example, here's one charge assignment that people have taken in the literature before, and you can verify that then CQ will have this structure. Lambda is this ratio and has to take on a value of order sine the Cabibbo angle. So this is just one example set of couplings that I'll be working with. And what you see here is a little bit different than in the anarchic scenario. Here, actually, yeah, let me point out. So on diagonal couplings, the flavor conserving couplings are not suppressed. They enjoy, order 1 coefficients. There's some order 1 number in front of all of these things. But the off diagonal, the flavor violating couplings are suppressed by a moderate amount. And so if you go over here, what you find is the axion that couples to tops in a flavor conserving way still has a C psi of order 1 and decouples at roughly this temperature. But the axions which talk to the top in a flavor violating way are suppressed by some power of lambda. And so you expect to get weaker constraints. Also, this k on decay bound gets a bit weaker. Also leptons, yeah. Right, yeah. It is not important, basically ever, for this particular.
Because the couplings is suppressed.
Oh, sorry, mu to E gamma. Yeah. The limit is lower. I think it's around 10 to the 8 or some 10 to the 9 maybe. In FA, yeah. So here the couplings to off-diagonal things are suppressed. So we do a bit worse, but also this k on decay bound gets weaker. And there's a possibility to, the broad conclusion is kind of the same. At high FA, the reheat temperature can't be as high as you maybe hoped. In the future, we could probably do maybe 2 orders of magnitude better. Good, and finally, the last assumption for flavor couplings we make is that the universe is described by minimal flavor violation, which essentially means that the only source of flavor violation in the universe is through the standard model Yukawas, which are of course the only flavor violation in the standard model. So what you do is you treat the Yukawas as spurions under the SU35 to the 5th flavor symmetry. And you also treat C psi as a spurion under this flavor symmetry, which means that you have to do an expansion in the standard model Yukawas. So this CQ, for example, has a diagonal element times some order 1 random number, and then there's a contribution that looks like y up dagger, and a contribution y down dagger, plus some stuff at higher order. When you do the Gram-Schmidt orthogonalization and so on, you find that this set of 6 couplings is the only thing that is ever actually important. So for things that couple to the top, there is a second order, really a first order contribution. But for everything else, only the identity matters. So this really suppresses the flavor violating couplings and of axions to the standard model. So of course, here I'm showing the decoupling temperature of various axions coupled to left-handed quarks and right-handed up quarks, and then other axions are suppressed by small Yukawas. And if we look at this density plot, essentially under minimal flavor violation, the k on decay constraints go away. But there are still really strong constraints from act, and with potential to do maybe 4 orders of magnitude better with future experiments. Good. So this is kind of nicely summarized in this plot here. Here I'm assuming that the decay constant is 10 to the 12 GeV, and as a function of reheat temperature, I'm plotting the number of axions which thermalize with the standard model and contribute to delta ineffective. So the constraints are shown with these solid and dashed black lines. And basically you can see the same thing that I just said. In the anarchic scenario, lots of axions are coupled, and successively lower numbers of axions are coupled to the point that eventually you need future experiments to see anything. So everything I said so far was at dimension 5, but at dimension 6, the EFT, well, as you get close to the scale FA in reheat temperature, the EFT breaks down, and you need to consider higher order couplings. So you can look at couplings at dimension 6, and it turns out that this is all you actually have to do. You don't need to go to dimension 7 or whatever. And that's because the structure of these couplings is just fundamentally different than at dimension 5. So there are only 2 operators you can write down. They're both a d phi squared times a standard model thing. So on the left, Higgs squared, and on the right, it's F mu nu. And this left operator has a symmetric Wilson coefficient matrix. You can diagonalize it, and you see that the couplings are given by the eigenvalues of this matrix, the eigenvectors of this matrix, so the axions that talk to the Higgs, like so. The right operator is antisymmetric in this matrix. So F mu nu is antisymmetric, and then I and J inherit that antisymmetry. You can do a kind of diagonalization where an eigenvalue lambda AF couples 2 different axions to the electromagnetic field. I guess this should really be B mu nu, because we're working above the weak scale. But what this does is, since it's quadratic in the axion field, both of these operators thermalize, or at least interact with the number of axions equal to the rank of these matrices. And so generically, if these matrices are just kind of random numbers, then you would expect them to be full rank. And so you would actually thermalize the entire axion spectrum. So even if there are 100 axions, all of them could be interacting with the standard model. And you can get really large yields depending on how many axions there are. So freeze-in contributions are also in principle important as well. So I'm just going to show one example here, because it's pretty model dependent. But this plot, density plot, is what you get if you take the gut axiverse. So at dimension 5, there's only basically the QC axion. But there are 99 other axion-like particles, which are coupled at dimension 6 only to the standard model. And the other assumption is that these numbers are order 1. And so if you get within a few orders of magnitude of the in reheating temperature of FA, then you can have delta ineffective, which is just massive, because every particle is talking to the standard model, which is really dangerous. And this depends on the number of axions that you imagine in the compactification, but is essentially independent of the details of the axion fermion couplings and so on. So in conclusion, I hope I've shown you that the phenomenology of the Axiverse is rich and pretty unexplored, like low-hanging fruit, like delta ineffective has kind of not been studied before. And through studying this, we found that reheat temperatures have to be relatively low in the Axiverse. Here, we've just been working within the context of an EFT, some top-down approach that kind of computes these Wilson coefficients would be great to have as well, to get less model dependence. But generically, you expect that you could get very large and effective signals in ongoing CMB experiments. And this approach should generalize to computing abundances of any large number of copies of any particle, which is something that might be interesting to apply to, for example, dark photons in the context of string theory. So that's all I have. Thanks very much for your attention. Oh, sorry.
One quick question for you.
Yeah.
So here the axions are talking to the strand, so the fermions. So can you mess up the light abundance in BBN? It's not enough.
Yeah, so generically the delta ineffective constraints from BBN are like a factor of 2 or so weaker than at the CMB. Yeah, so that depends on ineffective. So I think it's hard. I mean, if you wanted to do something like that, you could imagine there's some mass threshold between BBN at an MEV and the CMB at an EV. So like somehow you have a lot of axions that are of order KeV, say, and then they decouple at the KeV scale. So you have large delta ineffective at BBN, but not at CMB. The problem with that is then they are dark matter and probably overproduce generically. So I don't have a good model that does that. Generically, the CMB is stronger, I think. Yeah, they have a mass threshold in that range. That's right. Yeah. I think it's probably possible. If you have I think that's right. Yeah, if you have something in thermal equilibrium at sufficiently low temperatures, I think it's probably fine. Yeah, that's right. But we're not thinking about it. Yeah, thank you.